In Unit 11, students are now ready to develop a model of the atom that can explain the role of electrons in periodicity and bonding. However, one of the challenges in teaching atomic theory to high school students is deciding how sophisticated a model they need for this. The Bohr model does provide evidence of discrete electron energy levels, but we typically end up resorting to the octet rule for describing bonding. We say atoms want to have 8 electrons in an energy level, but without providing any real physical mechanism for why it must be 8. Yet the quantum model goes well beyond what high school students need, and even beyond what they are prepared to understand. We still often end up with a bunch of rules that have no better conceptual foundation for our students than the octet rule. In the last unit, we examined the Bohr model of the atom. In this model, the energy of the spectral lines of hydrogen provide evidence that hydrogen's electrons can be taken to higher discrete energy states. We also know that adding sufficient energy can remove the electron from the atom to form an ion. We now want to extend this model by examining elements beyond hydrogen. We begin this modeling cycle by investigating the energy needed to remove each electron from a given atom, one after another. This data is called the successive ionization energy of an element. Students use a table of the successive ionization energy data for the first 20 elements to look for trends within the data for these elements. In Investigation 1, the students began by plotting the ionization energy graphs for boron, silicon, and calcium. For example, we can make the ionization energy graph for silicon's electrons by highlighting its data column, including the element symbol, and then selecting a scatter plot in the Charts menu. Highlighting the element symbol along with the data will place the element symbol as a title to the graph. Looking at the graphs of boron, silicon, and calcium, students should notice that each graph has a distinctive pair of points near the top of the graph, with points near the bottom that may have groupings within them. However, the data are clustered closely enough that it is hard to know for sure if there are any common patterns between the graphs in this lower section. We would need to expand this section to better see how these points are organized. To do this, students may try to expand the vertical scale on the graphs to see more detail, but they will quickly find this makes it difficult, if not impossible, to see the full graph at once, especially for the larger atoms. Students can take a closer look at this lower section of the graph by changing the vertical axis to a logarithmic scale rather than the linear scale they now have. They will need to click on the vertical scale of the graph to open the Format dialog box with the Scale menu active. Now check the logarithmic scale option near the bottom and click OK. Students will now see that the scale is stretched out in the lower part of the graph to show more detail in the data, while the top is more compressed so they can still see the whole graph at once. Here are the 3 graphs displayed with a logarithmic energy scale. Students can now look for a pattern in the lower ionization energies between the 3 elements. As students identify a pattern in the ionization energies of these first 3 elements, they should be encouraged to test their hypothesis by looking at the graphs of other elements to see if their pattern is supported by additional data. For example, students will often decide boron has 3 groups of electrons, a group of 1 followed by a group of 2 and another group of 2. They must decide which elements they would want to examine to test their expected pattern. As we dialogue with the students during this investigation, it is helpful to reinforce that these are graphs of the energy that must be added to the atom to remove electrons against the proton-electron attraction. Students can be led to articulate this by asking what is different about the electrons represented in the bottom of the graph compared to those at the top of the graph. Some of our more observant students may note some subtle substructure in the blocks of 8 electrons. Here is a graph of the 3rd through 10th ionization energies for calcium. While this graph provides evidence of fine structure in the electron energies, it is beyond the scope of the model being developed. However, this observation might be explored further in an AP or honors level course if the quantum model of the atom is to be examined. In a regular high school course, these students can be encouraged for their keen observations, since, evidently, there is more to be explored and modeled in the structure of the atom.